On this question, we want to use the graph of a basic function and a combination of transformations to sketch the graph of the function. The function we're working with is g of x equals negative 1/3 absolute value of x plus 3 plus 1. The absolute value bars in our function gives us an indication that our base function is the absolute value function, which is y equals absolute value of x. So we want to take a moment to reflect on what the shape of that graph is. The graph with the absolute value of x is going to be a V-shaped graph, and that corner that's created by the V is going to occur at the origin where the x and y axis crosses each other. So that's going to be helpful as we look through our transformations and adjusting that graph to a new position, knowing that that corner occurs at 0, 0. So then I'm going to take a moment to analyze the different operations that are displayed in this function. So we have a negative, we have this 1/3, which is being multiplied. We have a plus 3, and we have, let's get one more color, this plus 1. Each one of these operations indicates a different transformation that occurs to the graph. Transformation meaning a change. So we're going to start with this V-shaped graph, and then we'll have changes or transformations based on what operations we see here. So when we're looking at these operations, there are 3 different operation categories that we're looking for. Adding and subtracting is in one group, and adding and subtracting indicates that we have a shift. So both of these, the plus 3 and the plus 1, are going to be shifts in the graph. The next category is to multiply by a negative. And when you multiply by a negative, you get a reflection. And then when you multiply by a number that's not equal to 1, we get either a stretch or compression. So then we want to narrow down what type of reflection, what type of shift, or what type of stretch or compression. And all of these transformations can be put into 2 categories, which are either horizontal or vertical. All of the operations that are inside of our base function, inside of the absolute value, are horizontal transformations. So the plus 3 is going to be a horizontal shift, and the other 3 operations are outside of the absolute value and will all be vertical transformations. So with a vertical reflection, that reflection will be over the x-axis. So I've gotten all the information I need about that transformation. For the stretch or compression, because I'm multiplying by a number that's in between 0 and 1, this is going to be a compression. So it's going to be a compression by 1/3. And that's because our number 1/3 is in between 0 and 1. A horizontal shift can either shift left or right. And because we have a plus, it's going to shift to the left. We're going to shift left 3 units because of that plus sign. A vertical shift can either shift up or down, and because it's a plus, it's going to shift up 1 unit. So this gives me an idea of what transformations to apply to our absolute value graph, to our V-shaped graph. I want to apply the horizontal and vertical shifts because that's going to change the location of our corner. So if I shift to the left 3 and up 1, my new corner will occur at the ordered pair -3, 1. The reflection, the vertical reflection, means that instead of the V facing up, it's going to face down. So I know just on the side that my V will go this way. And then the stretch, excuse me, this is a compression. This compression is going to compress vertically. So all of my Y values are going to be multiplied by 1/3. So let me explain that in a little bit more detail. So if I go back to this graph here, my base graph, we know where that corner occurs. It's at 0, 0. But then we have these 2 points here, which are 1, 1 and -1, 1. This compression is going to change those to be, change just the Y coordinate to be 1/3. So if we change it to be 1/3, that means that our V becomes a little bit wider. So when I draw this graph, I'm going to draw the next 2 points to be 1/3 down from where we were. And now we can see a sketch of our graph. So we have the graph of g of x equals -1/3 absolute value of x plus 3 plus 1. For this example, we want to follow the 9-step graphing strategy to sketch the graph of the rational function. Be sure to find all intercepts and equations of all asymptotes. Find any removable discontinuities. The function we're working with is f of x equals x squared minus 9 over x squared plus 4. So we're going to start with finding our domain or any restrictions that are going to be on this function. So to find the domain of a rational function, we set the denominator equal to 0 and solve. So here I have x squared plus 4 equals 0. I'll subtract 4 on both sides, and that gives x squared equals -4. I'll take the square root of both sides. And on the left, I get x, the square root and the square cancel. That's going to have me pick up a plus or minus symbol on the other side. And the square root of -4 is 2i. Now, because we got an imaginary number here, we haven't gotten any restricted values on our real number line. So since we didn't get real numbers, we have no restrictions. And our domain is going to be all real numbers. So we have no restrictions. And because there are no restrictions, that also tells us that there are no vertical asymptotes and also no removable discontinuities, because vertical asymptotes and removable discontinuities are going to occur at those restricted values. So since we have none, we will have no vertical asymptote and no removable discontinuity. The next thing we want to do is find any intercepts of the function. So I'm going to look for x-intercepts. And to find x-intercepts, you set y equals 0. We're using function notation, so we're going to set our function f of x equal to 0. That's going to give 0 equals x squared minus 9 over x squared plus 4. To solve this equation, we'll multiply by the denominator on both sides, and that will clear the denominator. So when I multiply by x squared plus 4 on the left, we're multiplying by 0, so we get 0. And when we multiply by x squared plus 4 on the right, the denominator will cancel, leaving us with the numerator. I can solve this by isolating the square. I'll add 9 to both sides. That gives 9 equals x squared. I'll square root both sides. And the square root and the square cancel each other out. I gain that plus or minus symbol on the other side. And we have a plus and minus 3. Square root of 9 is 3. So we have two x-intercepts, one at 3, 0, and the other at negative 3, 0. So then we'll look for y-intercepts. To find a y-intercept, we let x equal 0. So we're substituting a 0 into our function. That gives 0 squared minus 9 over 0 squared plus 4. 0 squared minus 9 would be negative 9, and 0 squared plus 4 is 4. So we have a y-intercept at 0, negative 9 over 4. Then we want to look for horizontal asymptotes. So let's rewrite our function up here. F of x equals x squared minus 9 over x squared plus 4. And when we're looking for horizontal asymptotes, we need to know the degree of the numerator. And the degree of the numerator will be the highest power on x. So that will be a 2. And we're going to call that n. So the degree of the numerator is n. And we want to know the degree of the denominator. So that's the highest power on x, which is also a 2. So we're going to call that m. And then we want to compare those values to decide what our horizontal asymptote is. Anytime the degree of the numerator is equal to the degree of the denominator, we know that the horizontal asymptote will be the equation y equals the ratio of the leading coefficients. So we also need the leading coefficients, and the leading coefficients are going to be attached to the highest degree term. So our highest degree term is x squared, and our leading coefficients are 1 and 1. So the ratio of those 1 over 1 is going to be 1. So this rational function has a horizontal asymptote at y equals 0. One more thing that might be helpful is to talk about symmetry. We can decide whether this graph will have y-axis symmetry, origin symmetry, or no symmetry at all by calculating f of negative x. So if I calculate f of negative x, I'm going to get negative x squared minus 9 over negative x squared plus 4. Negative x squared is x squared, and negative x squared is x squared. And that calculation got me back to the original function. So we found that f of negative x is equal to f of x, and this is our definition of an even function, and even functions have y-axis symmetry. So we know that the graph will be symmetric around the y-axis or have a mirror image going over the y-axis. So we want to make sure that we have that within our graph. So we're going to take this information that we've gathered and start to create the sketch of our graph. And so on my graph, I'm going to put down that I have a horizontal asymptote at y equals 1. Let's use red for the horizontal asymptote. I've also found some other details, which are the x-intercepts at 3, 0 and negative 3, 0. And also a y-intercept at negative 9/4, which is just a little bit less, 9/4 is just a little bit less than, a little bit more than 2. So it'll be about right here. So then we want to decide whether we have enough information to draw the graph. I know that the graph will be approaching the asymptote because we have that horizontal asymptote, but I might not feel confident about how to connect these 3 points to each other. So when that happens, what we do is we find a few extra points to plot. So in this problem, it was suggested to plot a few extra points, specifically these extra points. And this notation is written as an ordered pair, and we have an x of negative 4, and the y part is left for us to calculate. So we want to calculate f of negative 4. We're going to substitute that negative 4 into our function, which will give negative 4 squared minus 9 over negative 4 squared plus 1. Excuse me, plus 4. That's 16 minus 9 over 16 plus 4. 16 minus 9 will be 7, and 16 plus 4 would be 20. So 7 over 20 is a small value, and I kind of already drew the graph at that spot. Then in this next ordered pair, we have an x of negative 1, and we need to calculate the y part. F of negative 1, negative 1 squared minus 9 over negative 1 squared plus 4. 1 minus 9 over 1 plus 4 is negative 8 over 5. And negative 8 over 5 would be about right here. And then the last one, f of 4, is 4 squared minus 9 over 4 squared plus 4. That's 16 minus 9 over 16 plus 4. That's 7 over 20. So we've got over here. The other thing to keep in mind is that we did say that this has y-axis symmetry. So I can mirror this point on the other side. So for a positive 1 and negative 8/5, we have that mirror point. And now we're getting a very clear sketch of this graph. For this question, we want to find all vertical asymptotes and create a rough sketch of the graph near each asymptote. But when we're looking for vertical asymptotes, we need to first find any restrictions we have on this rational function. So we're going to do that by setting the denominator equal to 0. We set that denominator x squared minus 11x plus 28 equal to 0. And we can solve this quadratic equation by factoring. X times x would give us the x squared. 7 times 4 will give us 28. And we need both of these to be negative to create that negative 11 in the middle. And we can set each of these factors equal to 0. And that gives x equals 7 and x equals 4. So this rational function has some restricted values at 7 and 4. But those restricted values might not be vertical asymptotes. They could be vertical asymptotes, or they might be something called a removable discontinuity. So we need to check to see if this function has any common factors. The numerator is already factored into x plus 6, and the denominator, we factored that into x minus 7 times x minus 4. And you can see that we do not have common factors between the numerator and denominator. So that means that both of these are vertical asymptotes. So this function has 2 vertical asymptotes. And then we want to draw a rough sketch of the graph near each asymptote. So there are a couple ways that we could come up with this rough sketch. One of them is with something that we call a sign chart. So what we're going to do is we're going to draw a number line. And on that number line, we're going to put all of the factors, or not the factors, the zeros of the factors from the numerator and denominator. So we already got the zeros for the denominator, that's 7 and 4, but we also want to use the 0 from the numerator as well, which would be negative 6. We're going to put those numbers on this number line. That's negative 6, 4, and 7. I'm making sure to put them in order from smallest to largest because our number line goes from left to right, smallest to largest. And over here, I'm going to list the factors that we have. We have x plus 6, x minus 7, and x minus 4. Let me draw a little grid for these different factors. The one thing about these factors is that they are all linear factors. They all have a positive slope. So when a linear factor has a positive slope, the graph will change its sign. So on the left here, all the y values are negative. So that's to the left of your x-intercept, or 0. And to the right of your x-intercept, all the y values are positive. So I can make this sign chart based on that information. So let me I'm going to draw little vertical dashed lines on all of these numbers to separate out my number line. And for this factor of x plus 6, it has a 0 of -6, and it will change signs over that value. That value is the 0. So remember we said here it changes signs over the 0 or the x-intercept. So it's going to be negative to the left of that 0, but positive to the right of it. Then the next factor is x minus 7, which has a 0 of 7, so it's going to change signs over that 0. It will be negative to the left of it and positive to the right of it. Then we have a factor of x minus 7, which, oops, I wrote the same factor twice, so this should be x minus 4. And x minus 4 has a 0 of 4, and it will change signs over that 0. So to the left of it, we have negative, and to the right of it, positive. So we do that for each factor, and then we're going to multiply all the signs together. So if I multiply these three signs together, a negative times a negative times a negative will be a negative for that interval. We multiply these three signs together. A positive times a negative will be a positive. We're going to multiply these three signs together. A positive times a negative will be a negative. A positive times a positive will be a positive. Okay, so let me explain why we did all that work. We have our asymptotes at 4 and 7. And now I know that to the left of 4 we have a positive, and to the right of 4 we have a negative. So that's going to tell me that the y is going to go to infinity on the left and negative infinity on the right. And for my vertical asymptote of 7, I now know that on the left is a negative and on the right is a positive. And so on the left, the graph will go to negative infinity, and to the right will go to positive infinity. So if I were to sketch a graph near these vertical asymptotes, here's my coordinate plane. I'm going to mark 4 and 7, put vertical asymptotes at 4 and 7. To the left of 4, I'm going to positive infinity. To the right of 4, to negative infinity. To the left of 7, to negative infinity. To the right of 7, positive infinity. So that gives me a sketch near those asymptotes. So I showed you how to get those pluses and minuses from the sign chart. But if that is confusing or maybe too much work, you can also choose test points. So let me just get a different color here. So I could choose test points on either side of my asymptotes. So I want to choose a number that is smaller than 4, so maybe 3.9. And I want to choose a number that's bigger than 4, maybe 4.1. And I'll choose a number that is smaller than 7, 6.9, and a number that's bigger than 7, 7.1. And if we substitute these values into our original function, we should get the sign as well. So we can substitute f of 3.9. Let's get our calculator out to make this more convenient. Okay, so I've got my calculator here, and I'm going to substitute into the numerator 3.9 plus 6 divided by 3.9 squared minus 11 times 3.9 plus 28. And all we need to pay attention to is whether we get positive or negative, and we got positive, and that matches what we saw on our graph. Then we do it again for 4.1. So we have 4.1 plus 6 divided by 4.1 4.1 squared minus 11 times 4.1 plus 28. This time we got a negative. Then we do f of 6.9 we have 6.9 plus 6 divided by 6.9 squared minus 11 times 6.9 plus 28, and we got a negative, and then f of 7.1 gives us 7.1 plus 6 divided by 7.1 squared minus 11 times 7.1 plus 28, and we get a positive. So hopefully you see that that matches. We got positive to the left of 0, positive to the left of 4, negative to the right of 4, negative to the left of 7, positive to the right of 7. So we could get the same pluses and minuses, which tells us that the y goes to infinity or negative infinity. On this question, it says find the equation of all horizontal asymptotes, if any, of the rational function f of x equals 7x squared minus 5x cubed over 8x cubed plus 3x squared minus 2x plus 6. The way that we're going to find horizontal asymptotes is by finding the degree of the numerator and the denominator. So most of the time when you have a function, the polynomial in the numerator and the polynomial in the denominator are written in descending order. And so we tend to look at the first power that we see and say that that first power is the degree. But this problem is written so that the terms are not in descending order. The highest power is on the second term, so the degree of the numerator is 3. And we're going to call that n. Now the polynomial in the denominator does follow that normal convention of descending order. We have the highest power first, then the next highest, then the next highest, and the next highest. So this polynomial in the denominator has a degree of 3, which we're going to call m. So we have the degree of the numerator being 3 and the degree of the denominator being 3. Those are the highest powers on x. Then we're going to compare those degrees to each other. And in this example, the degrees are equal. The degree of the numerator is equal to the degree of the denominator. So we have memorized that when the degrees are equal, that the horizontal asymptote is going to be y equals the ratio of the leading coefficients. Now that word leading can mislead students to think that the coefficients in the front, the ones that are leading, are the ones that we use. But what we need to use are the coefficients that are attached to that highest degree term. So it's only leading when you write it in descending order. So we're going to use the coefficients from those highest degree terms, and we're going to get that our horizontal asymptote is y equals -5/8. The ratio of the leading coefficients. For this example, we're given the graph of a piecewise defined function, and we want to give the rule that describes this piecewise defined function. So as I'm looking at this graph, I notice that I have two pieces of the graph that look very different to each other. So that means that I'm going to have two equations to represent this. So with my piecewise defined function, it's going to follow this format. F of x equals, and I'm going to have two equations because I see two pieces of the graph, and those two equations will have two conditions that go with them. So each equation gets the conditions that goes with it. Now the conditions are what I like to start with because the conditions are on x. So if we focus on where this piece of the graph starts and stops, that's going to tell us what the conditions on x are. These x's are all in between an x of -7 and an x of -2. So an x of -7 and an x of -2. So my x condition will be between those x values of -7 and -2. I do want to pay attention to what's happening at the endpoints. I notice that both of them have these filled in circles, so both endpoints are going to be included in that equation. So I need to put equal to's on both of those to make sure that the endpoints are included. So then I'm going to focus on the conditions for the second equation. For the second equation, we have this arrow indicating that the line goes on forever. So I have no endpoint. On the other side, I do have an endpoint, which is at an x of -2. So these x's are from -2 and larger. So we can say more than -2. So with that condition, we're going to write x being greater than -2. I used, instead of x being between two numbers, I say x is greater than a number because this doesn't have an end to it. Once again, I want to pay attention to that endpoint, and this time the endpoint has an open circle on it. so I don't put an equal to on my condition. So now that I have my conditions, I need to figure out what those equations are. The second one is a little bit easier because it's a horizontal line. And the equation of the horizontal line is y equals whatever that y value is. Notice all the y values on this line are all 5. So 5 is the equation. Y equals 5, and we only write down the right-hand side in our piecewise defined function. The other one is going to take a little bit of work because we have a line. We can figure out the equation of that line because we have 2 points on the line. So we have 2 points, -7 and -1, and -2, 4. We can find the slope using the slope formula, y2 minus y1 over x2 minus x1. So I'll let this point be x1, y1, and this one be x2, y2. So we have 4 minus -1 over -2 minus -7, and that gives 4 plus 1 over -2 plus 7. So we have 5 over 5. So this line has a slope of 1. And then we can figure out the equation of the line by using point-slope form. Y minus y1 equals m times x minus x1. So I'll use the slope of 1 and this point here. I have y minus -1 equals 1 times x minus -7. That's y plus 1 equals x plus 7. I can subtract 1 to get y equals x plus 6. So the equation is x plus 6. And so now we have the rule that describes this particular graph. Thank you for checking out my videos. Have a great day.